has Zoom up. If anyone has Zoom up, can you tell us if this is working? But I'm otherwise assuming that it is.
It's probably working.
Sorry about that, everyone.
All right.
Good luck.
Yeah. All right. So yeah, I'm Chester Gould, all the way from UBC, and we're talking about a performance comparison, syntax, and type-directed judgmental equality. I guess a standard disclaimer for PL talks. If you don't know what one of those or many of those words mean, we'll get to it. Don't worry. Does this work? Almost certainly not. Good. All right. So I've come all the way across the Pacific to Singapore to answer one question. That question. So, when I was an undergrad, those many long months ago, I had to work on a research project that involved writing a type checker, specifically a type checker for a dependently typed language. But what is that? What is a dependently typed language? I'm assuming some of you know, but just a little, in case there's someone in the room who doesn't know, we're going to do a little dependently typed crash course. Yeah, all right. Cool. So consider this function. Super helpful. You might write this yourself. If you're trying to give this function that takes a Boolean, if it's true, returns 5, otherwise returns the string hello world, you might try and give it a type. But if you're working in a language like Haskell, you might have a bit of trouble doing that. But with the magic of dependent types, we can give it that type. This type says that if you give the function int string a Boolean, then it's going to return an int. Otherwise, it's going to return a string, just like it actually does. Wow. Okay, then we can do that to implement 5. We call it with true, should return 5. But maybe that's not enough for you. Maybe you want to prove that our implementation of 5 is correct. So we can do that. We can do that too. So we define another global variable, and notice that this is its type. So its type is a proof that the global variable FIVE is equal to the number 5. And then as our term that has this type, we use the reflexivity proof. But how does any of that work? Don't be alarmed, but yeah, typing rules. Okay, so what is this thing? Derivation rule. If the thing on the top is true, namely that we can judge that E and E prime are the same, they're the same expression, then we can judge that reflexivity has the type of a proof that E and E prime are equal. But that begs, well, okay, it begs probably more than one question if you're not familiar with dependent types. But one question it does beg is, what the heck is this? What does this mean? So intuitively, you should read this as saying that the expression E and E prime run to the same value. So when we say that we can use the reflexivity proof here, we're just saying that 5 and, well, variable 5 and the number 5, they already run to the same value. So we're saying that this is equal to that 5 there. So you might then wonder, well, how do we know if two expressions run to the same value? So we're going to introduce a few rules. One of them looks like this. This says that if you have an if expression where the predicate is true, then we can judge that to be equal to E, which is the expression in the then branch. We can specialize this rule to our program, a little snippet of it, and we can then judge that that expression that appears in our program is equal to 5. Then we can stack them on top of each other, just like that, and we can get a proof that the if expression in our program is equal to 5. Okay, wait, why did we do? We're on a little digression again. What are we doing that? What are we doing again, right? Yes, type checkers. So okay, you need to implement a type checker for a dependently typed language. You need to decide on an algorithm to use. Now, of course, being the good undergrad I was, I didn't just like go off and try and hack on something and just implement it, right? I did what all good undergrads love doing. I did a literature review. We love that, yeah. So if you do a literature review, you might happen across this paper by Cocon called An Algorithm for Type Checking Dependent Types. That's a very promising title if you're doing a literature review. So how this algorithm works is that it uses an equality judgment that looks exactly like the one we saw previously. And it works by doing structural recursion on both sides of the equality judgment. So if we were to want to decide if a function application, two function applications are equal, you can do structural recursion. And we first check if the two functions are equal. And then we check if we can judge the two arguments to be. All right, well, maybe, I guess if you're doing a literature review, you don't just stop at the first paper. I guess you could, but maybe I should have, but yeah, so another paper you might find is this one by Chapman, Alton Kirk, and McBride called Epigram Reloaded. And they have a slightly different take on what algorithm you should use. Yeah, we have one guy who knows already. So they use what's called a type-directed judgment, quality judgment. So it's sort of like before, except that we also have the type of the two expressions in the judgment. So this reads that E and E prime are judged to be equal at type A. That means they're both of type A. Now, we still have all our favorite rules, like the if true rule, where A here is just the type of E. But if we consider, since now that we have the type that we can consider, if we have some interesting type like the unit type, which has one inhabitant, open parenthesis, close parenthesis, that's it. That's the only thing of unit type. We can think that, well, any expression of unit type should run to the same value eventually. Therefore, we can add this rule that just states that everything of the unit type, they're just all equal. So, using our new type-directed judgmental equality, we can do this proof. So this says that this is a function, takes two units, and it outputs an equality proof that A and B are equal without even looking at what they are. So in the type-directed version, this type checks. It's green. It's great. But in the syntax-directed version, they do not. This does not type check because we haven't even looked at what A and B are, and so all the equality judgment sees is just two unrelated variables, and it says they're not equal. So that's just a little taste of how these two algorithms differ. They decide different equalities. Okay, so we have two algorithms. How do we decide which one to use? You might want to consider some of the trade-offs. Surely someone must have studied those, right? Trade-offs, yes. What are they? So there are two classes of trade-offs you might consider. The first being performance trade-offs. So why might we even think that there's a performance difference between these two algorithms? So in the type-directed version, we have this extra argument, the judgment, A, the type. And so you might think, well, on one hand, we now have more information for deciding if these two expressions are equal. And so maybe we could complete the search faster. But on the other hand, now we're processing a lot more information. So this might slow it down. What about the usability trade-offs? So we already saw that some programs will type check in one system, some won't in the syntax directive. But when does this appear in practice? When, is this actually useful to have these extra rules that we can decide? maybe, the unit type, it's a bit of a boring type. I don't know. Maybe this code might appear in your code base, but this is not the most interesting function of all time. So maybe there's more interesting types that have rules that the type-directed equality can decide. So without further ado, here's what the previous literature says. Definitively, the performance trade-offs are. No idea. No idea if it's slower or faster. There's lots of debate about this. People have very strong opinions about which one is faster. No evidence for either side. Okay, great. Usability trade-offs, though. Surely someone must have studied the usability trade-offs because some programs type check, some don't. Maybe we could find a practical program and show that type checks in one, it doesn't type check in the other. Well, previous literature also says triple question mark. We have no idea.
All these work's been done by theorists. So these
Yeah,
are
theorists.
questions that theorists
Yeah,
ask,
well,
so.
yeah. Well, we do love our theorists. Okay, so I will tackle first question. The usability question, that's a little beyond my pay grade. But so to do that, to decide to address the performance trade-offs, you need to do a performance comparison, right? I guess you could try and do a proof and stick to the theory and prove the complexity or something crazy like that. So we need to do a performance comparison. And that means we need two implementations, one of each algorithm. Luckily for me, someone had already implemented the syntax-directed version quite quickly. It's quite efficient. See, it says high performance right here. Yeah. So this is by, I'm sorry, I might butcher your name, and I don't know if he's in the room, but this is by Andras Kovacs. And yeah, so that's one. And so I'm gonna boldly and proudly lie to you all and say that this is the type of the equality decision procedure in small tt. So it takes an expression and another one and decides if they're equal. And so, as I said before, this proceeds by a structural recursion. And so we can just add maybe the add case from that rule we saw before. And yeah, we just do a recursion, check if f and f prime are equal, a and a prime are equal, and if they're both equal, then your app is equal. Easy peasy. So that's a syntax direct implementation done. That was, well, not much sweat on my part, but I'm left with wondering, what about the type-directed algorithm? Well, I implemented that. So I forked small tt, and I modified it, leaving all the optimizations that small tt does in as untouched a state as possible to make the comparison accurate. And in that implementation, my forked version, as again, lying to you all, this is the type of the equality decision procedure. So, like before, it takes two expressions, but now it also takes a type. And so, if we wanted to add that unit equal rule from before, we can just add it. We can just look at the type. If it's the unit type, great, they're equal. Super easy. So we have two implementations. Now we need to benchmark them. Yes. Hold on. Wait, we need a benchmark suite, right? I can't just, well, luckily small tt actually comes with that and it's pretty good. It's basically just some enormous files for you to type check. The church encodings of the simply typed lambda calculus, it's not super important. Don't worry about it. Okay, great. Benchmark suite. Benchmark them. So these are the performance numbers. And we have the syntax-directed algorithm normalized to 1 in red. Is that red? It's red, yeah. And then we have the type-directed algorithm in blue. And yeah, so definitively, from these, you can see that syntax directed is faster. 100%, right? The end. Good job. All right, we're done the presentation. No, I'm kidding. So these are the tentative performance numbers. This is definitely very much a work in progress. I did my best to keep all the optimizations, but the algorithm it's non-trivial, and honestly, small TT does a lot of other things that I'm just not telling you about, like unification and collaboration and all these things, and maybe my implementation missed something. So this is, yeah, still work in progress. As we can see here, this bar just keeps on going. It just goes off the screen. Yeah, this benchmark did not complete. I think it ran out of memory. Honestly, I'm not quite sure why. That's future work. I thought I knew, and then I was incorrect. Okay, so great. Yeah, future work. Okay, I don't want to be greedy. So honestly, this is our future work. So the first is to take the two implementations, small TT and my version of small TT, and just try and optimize them even more. Maybe I missed something, and the type-directed version could be made much faster than the syntax-directed version. I'm not sure. Some more future work is maybe your own pet favorite algorithm is not represented here, and you are so sure that it's gonna be way faster than the other two. Well, then you should go and implement it. You should also go and modify small TT or implement something else and show the world that you're right and it's faster. Okay, finally, I didn't address this question. That's honestly a harder question to answer than the performance question. So, wait, what are the usability trade-offs? We saw one rule that's different between the two systems. Is that rule really going to be so important in practice that two things of the unit expression are going to be equal? Probably not. So maybe, yeah, we need to address this, find some use. Maybe there is something that's really useful that you can do with the type-directed version that you can't do with the syntax-directed version. Finally, I would like to give a shout out to another project that's sort of doing a similar thing. This is the benchmarking proof assistance GitHub repo. If you really didn't like the approach I took and you want to go and contribute to the NbE, you can go and do that. And yeah, go contribute to their project instead of mine. Okay, great. Yeah, so in takeaway, you should know that trade-offs. You should know what you're doing when you're choosing between two algorithms, and instead of just being very opinionated about it. And yeah, great. If you're interested, there's more in the extended abstract, a little bit more. Yeah, thank you.
Thank you. And so we've got time for questions.
Do I get to choose? Yeah. I did. Yeah, we didn't even, yeah, I lied to you so much in this talk. I didn't even mention normalization, did I? But it's in the paper. Yeah, so I reused it. Yeah.
Your equals has an expression type to Gould, right?
Yeah.
You check that both expressions actually have the type before.
Yes. So yeah. So yes, you in the type checker, you first type check your two expressions.
Mm-hmm.
If you know, you have to know what their type is beforehand. Check that their types are equal.
Mm-hmm.
Using the same procedure because we're independent types and types are well, yeah. And then you get to check them. Yeah. Yeah. Cool. Any other? Oh,
Go ahead.
yeah.
So like this is just hearsay, but my understanding of András Kovács's work on small people is that like he doesn't just write the Haskell code, right? Like he actually looks at the core. There's a ton of micro optimizations that go into
Yes. Yes.
My question is, did you just write Haskell code, or did you try to put in the same effort? Because otherwise, there's a huge difference in the engineering effort between.
Absolutely. So yeah, so as I said, I totally lied to you about the type of that decision procedure. It's doing some stuff in the IO monad with mutable states. All his optimizations that he does, I did my best to port them to the type-directed version. And I did my best to not write slow code. I have some experience in Haskell. I tried my best, but I mean, honestly, I think that's the best answer. Yeah. Yeah. Of course.
Is it more efficient to would be combine the type checking with the pipeline? Instead of
Sorry, combining type checking with what?
what would you just said is given two expressions, first to the type checking for two expressions and the
I hadn't thought about that. That's an interesting idea. Implementing. Yeah, I mean, yeah, this is just sort of a propaganda, like get people excited about this sort of talk. So yeah, that's a great idea, and we should totally implement that. Yeah, sure. And then I'll get to you.
Just to follow up, so the type of your equality function or something expert, I know it's a lot,
Yeah.
it's like expert type Gould.
Yeah.
And like just the order of the parameters kind of suggests that you are looking at the terms, and then you might use the type information.
Oh,
to
okay, yeah.
make progress. But
Maybe I didn't mention. So yeah, so that algorithm, it proceeds by a structural recursion of the type first,
okay.
and then the expressions. Yeah, I guess it's Curry's. It suggests something. I'm not trying to suggest anything. I just wrote it that way. I think it's the same. It might be the other order in the actual. Yeah. You had a.
Just to note that you said that the unit type equality judgment is perhaps not that useful. So like but if you have proof irrelevance.
Oh yeah, proof irrelevance.
Lots of things that are basically unit types.
Yeah. Okay. There's one use case. Yeah. Okay. Yeah. But then that sort of begs the question: is proof relevance useful? I'm not saying either way. You just yeah.
You have a type code thinking. You have a type code equal function type.
Yeah. There's a. It's just the like eta rule. It actually turns out that both systems can decide specifically for function types and for the dependent pairs. They can decide the stronger eta equality for both of them. But it doesn't work for unit types. And it doesn't work for, there's some other types like coproducts. Yeah. Did we do it?
All right.
Yeah, answer. Yeah.
Thank you.
Thanks.